So in the last section we talked about Laplace expansion, and in this section I want to use Laplace expansion a little bit to talk about matrix adjoints, or sometimes called adjugates. So let's just jump right into the definition and then see some examples and how all this stuff is useful. So the matrix adjoint, sometimes called the adjugate to the square matrix T, is given by the following formula. So it's the notation is adj of T, and the entries are the cofactors, the ij cofactors of the matrix T. So T11, remember this would be so it would be positive because -1 to the 1 plus 1 times the determinant of the 1, 1 minor of T obtained by deleting column 1 and row 1. And then T12 would be the same sort of thing. It would be the 1, 2 cofactor. Except here's the thing, you have to be careful with this. So T12 is the that is the cofactor. So you delete row 1 and column 2. So row 1 and column 2 looks like that, but we're looking at T12. So it's not exactly what you would expect it to be. All of the indices are reversed here. So you could also think of the adjugate as being equal to, so let me just do T11, T22, T12, T21, where everything is like as you would expect it to be, Tn1 up through Tn, except at the end you just take the transpose of this matrix. So these things actually are equal. Let me back up because this is being weird again. Anyway, cool. Nope, wrong one. Here we go. Okay. So yeah, the adjugate or the matrix adjoint is given by it's the matrix consisting of all of the cofactors, except you transpose it at the end. Okay. Here's why the adjoint is useful. It's because we can use the adjoint to derive a formula for the inverse of a non-singular matrix. So here's how. First things first, here is equation 1. That'll be useful. So Ti1, Ti times capital Ti1. So this is the I1 entry of T, and Ti1 is the I1 cofactor of T, and so on and so forth. So this half of the equation, this side of the equation, represents cofactor expansion along row I of the matrix T. And cofactor expansion says that this expansion is equal to the determinant of T. So this equation is true just by the cofactor expansion theorem. Okay, there's one more equation that we need for this. And for that equation, first things first, just recall that if a matrix M has row I and row K equal in that matrix, then that the determinant of that matrix must be 0. So here's why this is useful. So for I not equal to K, the sum Ti1 capital T K1 plus Ti2 capital T K2 plus Tin capital T Kn, this represents expansion along row K of a matrix with row I equal to row K. And reason being, we're like, if row I and row K are equal, then we want to think of row I as being equal to Ti1 up through tin. So ti1, ti2 up through tin. So rho I and rho k are equal. And so all of these i's could be replaced with k's, and so in this sum right here, all of these i's could be replaced with k's, and so this entire expression right here represents the determinant of a matrix with rho I equal to rho k, right? So this, so here we are, this is important because this tells us that this whole thing is equal to 0 because it is the determinant of a singular matrix because it has two rows equal to each other. Okay. Sorry, I don't want to repeat myself too much there. But anyway, this is this guy. So let's call that equation 2. So if we take equation 1, which says this one, and let me like bring that down here. Let's copy that. And let's just bring that down a little bit. So let's combine equations 1 and 2. We get the following. So this is for all I equal to 1 through n. And so I could take all of these equations and throw them into a product of matrices here. So if I do row 1 times column 1 of this matrix right here, then that gives me ti1, ti2, etc. times capital Ti1, capital Ti2, etc. And this right here is the matrix adjoint. This right here is the adjoint of T. And therefore, so like the 1, 1 entry would be by equation 1 equal to the determinant of T. And then similarly, the 2, 2 entry would be equal to the determinant of T, because I would have T21 times capital T21, small t22 times capital T22, so on and so forth. Again, that comes from equation 1, and then that would hold for all of the diagonal entries. And then for the off-diagonal entries, I would have, let's do like, for example, row 1 times column 2, I would have, well, maybe let's do like column n. Then I would have ti1, ti2 multiplied by tn1, tn2, and then that would give me, so t11 times tn1 plus t12 times capital T n2. And so this is giving me exactly equation 2 here, just with I is equal to 1 and K is equal to N. And therefore all of our off-diagonal entries should just be equal to 0 here. Okay. So this is great. Keep in mind, this does not assume anything about T being invertible. This is just a generally true thing that holds for any matrix T, that if you take the matrix T here and then form the adjoint of T, and you can always form the adjoint. Every matrix has an adjoint because the cofactor has nothing to do with whether or not your matrix is singular. Like, you can always form this matrix. this product times this, this matrix times this matrix is always equal to this matrix. But if the determinant of T is equal to 0, then this whole matrix is the 0 matrix. So if T is not invertible, then T times the adjoint is equal to 0 in that case. And if T is invertible, then you could still factor out T times the identity matrix. Factor out T, you're left with the identity matrix. And therefore, the determinant of T is a constant, so I could just divide by that on both sides. And that thus tells me a formula for the inverse of the matrix T. So the next theorem just summarizes all the things that I was kind of rambling about for maybe a little bit too long, sorry. But so here's the theorem. For a square matrix T, T times the adjoint is equal to the adjoint times T. I didn't actually like show this part is true, but the the reasoning works out just the same as like what we talked about before. So both of these things are equal to the determinant of T times the identity matrix as we had up here. And if T is an invertible matrix, then T inverse is equal to the reciprocal of the determinant times the adjoint. You just divide the adjoint by the determinant of T. Okay. All right, so let's do an example. Make this a little bit more concrete. Let's use the adjoint to find the inverse of the following matrix. So A is equal to 1, 4, 2, 0, 1, 0, 2, 1, 3. So first things first, what is the determinant of A? Well, I could just do cofactor expansion on row 2 here because I get a bunch of zeros. So I get negative 0 times something plus 1 times the determinant of 1, 2, 2, 3, and then minus 0. And so this is equal to 3 minus 2 times 2 is 4. And so the determinant of A is equal to negative 1. So this is actually an example where cofactor expansion is pretty useful for finding the determinant of this matrix because we had a row with a bunch of zeros, and that made finding this determinant really easy. Okay, so now let's do the adjoint. Finding the adjoint can be a little a little time consuming sometimes. Let's do it. So I'm going to copy and paste this over here so that I have a smaller thing over here that I can look at. Okay. So the adjoint of A is equal to, all right, so I'm going to take a bunch of cofactors here. So the 1, 1 cofactor is positive 1, 0, 1, 3. Okay. The 1, 2 cofactor, so delete row 1 and column 2, and that would, and it should be negative 2. And then I have the determinant of 0, 0, 2, 3. You might say that, oh, hey, this should be over here, but I think it makes a little more sense to put everything in the place where you sort of expect it to be, and then just take the transpose at the end. I think it's a little bit easier to keep things in mind that way, keep things straight. So anyway, let's do that. Let's do the 1, 3 adjoint next. That'll be positive 1 times the determinant of 0, 1, 2, 1. All right, there are 9 of these, so I'm going to start going faster. 2, 1, that'll be, this one has to be negative. 4, 2, 1, 3. What's next? I'll have 1, 2, 2, 3. And then I have, this will be negative 1, 4, 2, 1, that determinant. And 3 more. Whoop, not that. Delete row 1, column 3. I get 4, 2, 1, 0. And then 1, 2, 0, 0. This one should be negative. And last one will be positive 1, 4, 0, 1. Okay. And so this is almost my adjoint, but I put everything in the place where I expected it to be, so I should take a transpose at the end. Okay. Cool. So now let's just calculate all of these determinants and then take a transpose. I'm going to calculate the determinants first and then take the transpose. So first determinant is 3 minus 0. 2, 1 entry will be 0. The next one will be 0 minus 2. Next entry will be 12 minus 2, which is 10, except I make it negative. Next entry is 3 minus 4, which is negative 1. Next entry is 1 minus 8, which is negative 7, but I make that positive because of the sign change. And then next entry will be 0 minus 2, and then that determinant is 0, and then the last determinant is 1, and then I take a transpose, and I get 3, 0, negative 2, 10, negative 1, 1, 7, 0, negative 2. And I think that is hopefully right. I don't know if this is right or not. I don't think that there is a easy way to check that it's right other than just going through the check of let's multiply these matrices together and see whether or not I get 1 over the determinant times the 3 by 3 identity matrix. So let's hope that that's what we get. I always do this because whenever I am figuring out adjoints, I think it's very common to make mistakes. So I always do this check. I did this check before I did this video and I actually got it wrong and then I corrected it, and so now I'm filming this video now, and hopefully this is the first take. Hopefully there's not a second take where I mess this up. But let's see what we get. Let's see. So row 1 times column 1 would be 3 plus 0 minus 4. Oh, that's good. Okay, what's my 2, 1 entry going to be? Well, if I get 0 plus 0, okay, that one's just going to be 0. What about 3, 1 entry? That'll be 6 plus 0 minus 6. That one is 0, so I'm happy with that. All right, what about row 1 times column 2? I should get negative 10 minus 4. That's negative 14. Plus 14, plus 2 times 7. That's 0. Next one will be 0 plus 1 times negative 1 plus 0. And then 2 times negative 10 is negative 20. Minus 1, negative 21, plus 21 is 0. Okay, great. I'm just going to go through the last one pretty fast because at this point I'm pretty confident this is going to work. Okay, negative 2 plus 0 plus 2, that's 0. 0 plus 0 plus 0, that one's 0. Negative 4 plus 0 plus 3, that's -1. And of course, this is equal to -1 times the identity matrix. And so that worked. So all of that worked. Therefore, A inverse is equal to 1 over the determinant of A times the adjoint of A, which is, so 1 over -1 is equal to -1. So I'm just taking the negative of the adjoint of A, and so I can just take this and make I can just change all of the signs of the entry, and then we'll be done. And that's how you do it. Positive, negative, negative. Okay, and that is our inverse. Great. So that's all for this section. Thank you for